Hi, welcome back. In this video, we're going to look for absolute extreme values of a function on a closed interval. So first, let's remind ourselves about the extreme value theorem and what that says. So the extreme value theorem says that if you have a continuous function on a closed interval, so f is continuous on the closed interval from a to b, then it has to have both an absolute maximum and an absolute minimum value on that closed interval. All right, so remember we looked at where those things happen. So absolute maxima and minima can occur at some local maximum or minimum, or it could occur at the endpoint of the closed interval. So that's what we're going to check. We're going to check the places where we might have local extreme values, and we're also going to check the endpoints of the closed interval. So these are the steps we're going to follow. This is how we look for absolute extreme value on a closed interval. So we first find all the critical numbers of the function. Remember, those are numbers in that interval where the derivative is either 0 or it doesn't exist. And then we're going to plug those numbers into the function. Plug the critical numbers into the original function to see what the y values are. And then we're also going to plug in the endpoints. So plug in a and b and look at those y values. And then we're going to compare all the numbers that we got in step 2 and step 3. And the largest of all those numbers is going to be the absolute maximum value, and the smallest of all those numbers is going to be the absolute minimum value. Let's do an example. So let's find the absolute maximum and absolute minimum values of f of t equals the square root of t over 1 plus t squared on the closed interval from 0 to 2. So first of all, we're going to find the critical numbers. So we have to differentiate the function f. So we're going to use the quotient rule. So f prime of t is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. All right, we do have to simplify this a little bit so that we can see where it's equal to 0 and where it doesn't exist. So it looks like a complex fraction, so I'm going to multiply top and bottom by the denominator, 2 square root of t. So when I do that, in the top, I get 1 plus t squared minus 4t squared. In the bottom, I just get 2 square root of t times 1 plus t squared squared. All right, and simplifying the numerator just a little, I get 1 minus 3t squared over 2 square root of t times 1 plus t squared squared. All right, so now the critical numbers are going to be any numbers that make the derivative not exist, or numbers that make the derivative 0. So when we look at the derivative, it doesn't exist only at numbers that make the denominator 0. And the only way the denominator could be 0 is at t equals 0. So t equals 0 is a critical number because it's in the domain of the original function, but the derivative doesn't exist there. All right, so where is the derivative equal to 0? Well, we have to set the numerator equal to 0 and solve that. So 1 minus 3t squared is equal to 0 when t squared is 1/3. And that means t is either positive 1 over square root of 3 or negative 1 over square root of 3. But only the positive 1 is in the interval, the closed interval from 0 to 2. So that one is a critical number. So we have two critical numbers, t equals 0 and t equals positive 1 over square root of 3. All right, step 2. we're going to plug in the critical numbers. So we're going to find f of positive 1 over square root of 3. We're going to plug it into the function, not the derivative. And then we're going to plug in 0 into the function. And then in step 3, we're going to plug in the endpoints. Well, 0 was one of the endpoints. So 0 is a critical number and an endpoint. The other endpoint is 2. So we're going to plug that one in. So we're going to get 3 numbers, and we're going to compare. So for f of 1 over square root of 3, that's going to be the square root of 1 over square root of 3 over 1 plus 1 over square root of 3 squared. And now when I simplify, this is 1 over the 4th root of 3 over 1 plus 1/3. So I got to simplify further, and when I get it all simplified, I can write it as 3 to the 3/4 over 4. You can fill in the steps. There's a little algebra to get that final answer. And now this number, it's going to be hard to compare it to the other numbers that we're going to get. So when I put it into my calculator, I can get a rough estimate. The rough estimate is it's about 0.57. All right, so now let's plug in 0 into the original function, and we get the square root of 0 over 1 plus 0 squared, and that's just 0. And then the last one, we're going to plug in 2, so the square root of 2 over 1 plus 2 squared. Simplifying that, I get the square root of 2 over 5. And now I want to compare these 3 numbers, so I'll put this one into my calculator and get a rough estimate. Oh, it's about 0.283. So now I'm going to compare these 3 numbers. So step 4 is to pick out the largest and pick out the smallest of all the candidates that we got from steps 2 and 3. So the absolute max is the largest of the 3 numbers we got, which is 3 to the 3/4 over 4. And if we want, we can rewrite that as the 4th root of 27 over 4. And then the minimum is the smallest of the 3 numbers, and that one was 0. So that's it. We look for critical numbers, plug those into the function, and then plug in the endpoints into the function, and then we just compare. We pick out the smallest and the largest. That's it for extreme values, and in the next video we'll talk about the mean value theorem and Rolle's theorem.